So one of the different ways that we can actually calculate, we just did this example of the Ruth Hurwitz criteria to figure out what's our margin or what's our critical gain to make sure that we're stable in the system. One way you can actually look at that or calculate that value too is by actually looking at a Bode plot. So what we can actually do is we can transform our function from the S to the frequency domain. And we can calculate our critical gain, which will be basically the inverse of the magnitude at that kind of critical frequency. And the critical frequency is going to be when we hit that phase lag of plus or minus 180. So when we are basically out of phase, essentially, with that system, at that angle, we're going to figure out what our magnitude is. So from the Bode plot, analytically, and then we'll calculate essentially that critical gain and to make sure that we're stable. So let's do an example. I need to update my notes of this. So for example, we are going to look at, this is our function. So let's say we have a function that looks like this. This is our L of S. So I want to look at my Bode plot. So my Bode plot right now, what I can see is that I hit minus 80 about, what is it? At a frequency of about 2.46. So let's see if that is true. So what we're going to do is we're going to calculate. Here, we're going to find essentially that, what's the omega when we get minus 180? It's indeed 2.44. Now, if I go up here and if I go to 2.44 frequency, I get a decibel value of about minus 9.32. So let's say I do minus 9.32. Remember, decibel equals 20 log 10 of magnitude. So that was our decibel reading from here. Now we're going to convert it to essentially the magnitude. We get a value of 0.344. Let's actually solve that analytically. And pretty close, right, from just looking on the plot. And the inverse will show us it's the critical value is 3, which is exactly what we found with our kind of analysis here. So pretty cool. And I also want to kind of show you before. So remember when we, it's kind of hard to see on the plot, like it's kind of exaggerated. It's also hard to kind of understand like where we are on the axis as well. So like that's 3, but we're getting pretty close to that boundary. It's just kind of showing us. But what we can actually see is if we put, actually, let's just make sure we're still in GS Simple. Yeah. If I put a value of 2 here, let's look at this numerically. So you see here, all my poles, I'm fine. Once I get to 2.9, let's see where we're at. We're getting close to 0 and 0 here. Once we hit 3, we're marginally stable. We're right on that borderline, right? 0. Our poles are lying exactly on that curve. And what do we see here? If we go just to 3.1. Uh-oh, positive, game's over. So that's essentially how you can look at and use this as a tool, the root locus, for trying to find essentially stability and critical gain. So what we're going to do, we're on our last lecture. So next time we're going to get into an experiment and actually explore this more, this idea of using and leveraging our frequency response and Nyquist to look at Nyquist stability criteria and then further examine Bode plots. So we'll see you in the next video. Thanks. Bye.